Dear students, now let us take the second application of the Gauss theorem, the electric field due to the uniformly charged infinite plane sheet. So we are going to find out the electric field due to the uniformly charged infinite plane sheet. In this diagram, the infinite charged plane sheet is given. Now we are drawing the imaginary Gaussian surface and Gaussian cylinder to find out the electric field at the given point P and the P dash. So first of all, we consider the surface charge density of the plane sheet. Here surface charge density is given by the charge per area. So Q is given by sigma into A, where sigma is the surface charge density. Now this Gaussian cylinder has a curved surface area, as well as at the end P and P dash there is a circular area. So on the curved surface area, what is the flux coming out from the curved surface area? So from the curved surface area, the area is in this direction and the electric field is in the horizontal direction in the figure. So electric field and the area, they are perpendicular to each other. We can assume it by using this pen also. Here this is the curved surface area of the pen. It is like a cylinder. So the area of one portion of the curved surface area is in this direction and the electric field is in horizontal direction. So electric field and the area, they are perpendicular to each other. So the flux coming out from this curved surface area is given by integration E dot dA is equal to E dA cos 90, and cos 90 is 0, hence integration E dot dA is equal to 0. So the flux coming out from the curved surface area is 0. Now the distance from the plane to the P point and from the plane to the P dash point is equal distance. Here as you extend the distance, then also we get the P and P dash point are at the equidistance, because here we are using the infinite plane sheet. Now the flux coming out from the P point and the P dash point is given by integration E dot dA. So integration E dot dA is equal to E integration dA is equal to EA. Same way at the P dash point, flux is equal to phi P dash is equal to integration E dot dA is equal to E integration dA is equal to EA. Now total flux is given by flux at the P point plus flux at the P dash point plus flux of the curved area is equal to EA plus 0, that is 2EA. So the first equation we get flux is equal to twice EA. Now second equation using same Gauss theorem, flux is equal to integration E dot dA is equal to sigma q upon epsilon 0. So here sigma q is the total charge. It is the total charge. So equation is q upon epsilon 0. Now here the total flux is equal to twice EA. So we can write twice EA is equal to sigma A upon epsilon 0, as Q is equal to sigma A. Here the Q is equal to sigma A. So the equation here 2EA is equal to sigma A upon epsilon 0. That means 2E is equal to sigma upon epsilon 0 and E is equal to sigma upon twice epsilon 0. So this is the final equation and it indicates electric field due to the uniformly charged infinite plane sheet. If we write electric field in terms of the unit vector, then we can write vector E is equal to sigma upon twice epsilon 0 into unit vector n, where unit vector n is in the direction of the electric field. As in this equation, the distance, this distance is not coming, that means the electric field is independent of the distance perpendicular distance from the plane sheet. Here we are taking, this is the distance, and this distance is perpendicular distance from the given infinite plane sheet. So electric field is not depend on this distance, because here we are taking the infinite plane sheet. This is, so the final equation is E is equal to sigma upon twice epsilon 0 into unit vector n. If we are taking the negative charge plane sheet, then electric field, for the negative charge, electric field is inward. It is in this direction for the negative charge. But for that also the electric field equation is same, sigma upon twice epsilon 0. Now we are taking the another application in which we are finding the electric field due to the thin spherical cell, which is the charged spherical cell. Now let us take the third application of the Gauss theorem, that is the electric field due to the uniformly charged thin spherical cell. So here we have taken the one thin cell. This is the thin cell. It is empty inside. We can take like a plastic ball, metallic ball or the plastic ball. So on this cell the charge is uniformly deposited. The plus that is the charge, it is uniformly deposited. This spherical cell is having the radius capital R. So we can take the surface charge density. So surface charge density is given by sigma is equal to Q upon area. So Q is given by the sigma into area, and it is also taken as the sigma Q. That means the total charge on the area of the thin cell is equal to sigma into 4 pi capital R square. Now to find out the electric field inside the cell, outside the cell and on the surface of the cell, we are going to use the Gauss theorem. So first we are taking the inside spherical cell, electric field inside the spherical cell. So inside the cell, at any point if you draw the Gaussian surface, so inside the cell at any point we get the total charge 0, because inside the cell there is no charge exist. So using the Gauss theorem, integration E dot dA is equal to sigma Q upon epsilon 0 is equal to 0 upon epsilon 0, that is the 0. That means electric field inside cell is always 0. Now the second condition, if we take the point outside the cell, let us take this is the point P which is outside the cell. So outside the cell at the point P, what is the electric field? At that point P, if you draw the one unit area, then it is in the same direction of the electric field. So E and dA, they are in the same direction. Now from the center of the cell to the P point outside of the cell, the distance or the radius is taken as the small r, where small r is greater than equal to capital R. Let us take r greater than capital R. So consider the P point outside the cell, draw the imaginary Gaussian surface. Using the Gaussian theorem, we can write phi is equal to integration E dot dA is equal to sigma Q upon epsilon 0. That means E integration dA, because E is constant, uniform electric field intensity. So E integration dA is equal to Q upon epsilon 0. So here we are getting the two equations for the electric field using the Gauss theorem. First, E integration dA is equal to E into 4 pi small r square. Small r is the radius of the Gaussian surface. So E into 4 pi small r square is equal to Q upon epsilon 0, where Q is the charge enclosed by the Gaussian surface. So this is the charge which is enclosed by the Gaussian surface, this one. So E is equal to Q upon 4 pi epsilon 0 r square. That means it is kq upon small r square, where r is greater than capital R. This is the first equation. Now here the charge q is given, but sometimes what happens that the charge is in large amount. So we consider the surface charge density. So this equation we can represent in terms of the surface charge density. So now using the Q is equal to surface charge density sigma into 4 pi capital R square, where capital R is the radius of the given spherical cell. So E is equal to Q upon 4 pi epsilon 0 R square is equal to sigma into 4 pi capital R square upon 4 pi epsilon 0 into small r square. So 4 pi is cancelled and we get the electric field E is equal to sigma upon epsilon 0 into capital R square upon small r square. This is the second equation, and this is the electric field outside the spherical cell. On the surface of the cell we can get small r is equal to capital R. So by putting small r equal to capital R, we get the E is equal to kq upon capital R square. So that is the electric field on the surface of the spherical cell. Now we can draw the electric field versus distance graph also here. So to draw the electric field versus distance graph, it is like this. Here we are taking the electric field on the y-axis, and here we are taking the distance. Start from the 0. Here this is the 0 point. We can take the small r is equal to capital R at some distance. So 0 to r is equal to capital R. Here this is the inside cell portion. So inside the cell the electric field is 0. Then on the surface, this is the surface. On the surface the electric field is kq upon capital R square. So that is the maximum value, E maximum. So here we get the E maximum. This is the E maximum point, E maximum. After then, outside the surface the electric field is proportional to 1 upon R square according to this first equation. So here we get the decrement of the graph. So here E proportional to 1 upon R square. So this graph shows electric field due to the uniformly charged thin spherical cell. So at the end of this chapter, let us take the surface charge density, linear charge density and the volume charge density concept. Actually we are taking the linear charge density, that is nothing but the charge per unit length. Okay, surface charge density, it is the charge per unit area, and the volume charge density is given by the charge per unit volume. So we can write the equation for the linear charge density. Lambda is equal to Q upon L. So it is the charge per unit area. Second, surface charge density. Sigma, read as a sigma, is equal to Q upon area. That is the charge per unit area. And third one, volume charge density. So volume charge density is given by the rho is equal to Q upon volume, that is the charge per unit volume. Charge per unit volume. So when we are taking the wire, the charge wire, and it is the uniform charge distribution, this we are using for uniform charge distribution. So only when we are taking the uniform charge distribution, then only we are using this linear charge densities, surface charge density and the volume charge density. If there is a wire given, charge wire, then we are using the linear charge density. If there is a area given, plane or the plate is given which is the uniformly charged, then we can use the surface charge density. If there is a sphere is given, hard sphere is given, which is the charge sphere, then we are using the volume, that is the volume charge density. Now in the next session we will take the some exercise question, and we will solve this exercise question and we will end the chapter. Okay, thank you.